The National Electrical Code does not explicitly prohibit grounding to a screw on a receptacle cover. However, there are indirect implications that suggest this practice is not recommended. NEC Section 250.148 states that equipment grounding conductors shall be connected to the equipment grounding terminal or the grounding bus in the enclosure. This implies that grounding connections should be made to a dedicated grounding point rather than a random screw. NEC Section 404.9b requires that receptacle plates be grounded in accordance with NEC Section 250.148, which further implies that the grounding connection should not be made to a random screw. There are risks associated with grounding to receptacle cover screws. Firstly, the screw on a receptacle cover is not designed to be a reliable grounding point and can become loose over time, creating a potential safety hazard. Secondly, the screw may not be made of copper or other highly conductive material, which can result in high resistance and reduce the effectiveness of the grounding system. Thirdly, over-tightening the screw when making the grounding connection can damage the receptacle. The recommended method for grounding a workbench on an Air Force base is to connect the grounding conductor to the grounding bus in the building. This provides a low-resistance, reliable path to ground and meets the requirements of the NEC. The grounding bus with 0.16 ohms to ground is an acceptable grounding point. When dealing with electrical systems and grounding, it's important to understand the underlying principles and requirements outlined in the National Electrical Code. While the NEC doesn't have a specific statement forbidding grounding to a receptacle cover screw, the intent and broader context of the code strongly discourage this practice. To fully understand why, let's delve into the details of grounding, the relevant NEC sections, and the potential hazards associated with improper grounding methods. Grounding, in electrical terms, is the process of creating a low impedance path for fault current to flow back to the source. This path helps to ensure that overcurrent protective devices, such as circuit breakers or fuses, will quickly trip and de-energize a circuit in the event of a ground fault. A ground fault occurs when an ungrounded conductor or hot wire comes into contact with a grounded surface such as a metal enclosure or a grounding conductor. The purpose of grounding is to protect people from electric shock, prevent fires, and minimize damage to equipment. The NEC provides comprehensive guidelines for grounding and bonding electrical systems. Grounding refers to connecting the electrical system to the earth, while bonding involves connecting various metal parts together to create a continuous electrical path. Both are essential for safety. Now, let's examine the NEC sections mentioned earlier and how they relate to the practice of grounding to a receptacle cover screw. NEC Section 250.148 is a key provision. This section focuses on connecting equipment grounding conductors, often referred to as EGC, to specific points within an enclosure. It mandates that EGC be connected to the equipment grounding terminal or the grounding bus inside the enclosure. The language here is important because it implies a designed and designated grounding point. The intention is that grounding connections should be made to terminals or buses specifically designed and tested for this purpose, not to any available metal part. A receptacle cover screw is not designed to be a reliable grounding point. Receptacle covers are often made of plastic or thin metal, and the screws used to attach them are not intended to carry fault current. Using a receptacle cover screw for grounding introduces several risks. These include the potential for a loose connection, which can increase resistance and impede the flow of fault current. It also includes the fact that the screw may not be made of a conductive material, which can further increase resistance. And lastly, over-tightening the screw can damage the receptacle, compromising its safety and functionality. NEC Section 404.9b further reinforces the importance of proper grounding for receptacle plates. It stipulates that receptacle plates must be grounded in accordance with Section 250.148. By referencing Section 250.148, this section underscores that the grounding connection should not be made to a random screw, but rather to a designated grounding terminal or bus. The requirement for grounding receptacle plates is intended to prevent shock hazards. If a hot wire were to come into contact with an ungrounded receptacle plate, anyone touching the plate could receive an electric shock. Grounding the plate ensures that any fault current will be safely conducted back to the source, tripping the overcurrent protective device. Let's discuss the specific risks associated with grounding to a receptacle cover screw in more detail. The first risk is a loose screw. The constant vibration and mechanical stress in an electrical system can cause screws to loosen over time. A loose screw creates a high resistance connection, which can impede the flow of fault current. In the event of a ground fault, this high resistance can prevent the overcurrent protective device from tripping quickly, increasing the risk of electric shock or fire. The second risk is poor conductivity. Receptacle cover screws are often made of steel or other non-conductive materials. These materials have a higher resistance than copper, which is the preferred material for grounding conductors. Using a non-conductive screw can significantly reduce the effectiveness of the grounding system, making it less likely that a fault current will be safely conducted back to the source. The third risk is damage to the receptacle. Applying excessive torque when tightening a screw can damage the receptacle, potentially cracking or breaking the plastic housing. This damage can compromise the receptacle's insulation and increase the risk of electric shock. In addition to these risks, grounding to a receptacle cover screw can also create confusion and make it difficult to troubleshoot electrical problems. A qualified electrician will typically expect to find grounding connections made at designated grounding points, not at random screws. Now let's turn our attention to the recommended method for grounding a workbench, particularly in a setting like an Air Force base where safety and reliability are paramount. The best practice is to connect the grounding conductor from the workbench to the building's grounding bus. The grounding bus is a dedicated conductor or bar that serves as the central grounding point for the electrical system. It is typically connected to the earth through a grounding electrode system, such as ground rods or a metal water pipe. Connecting the workbench to the grounding bus provides a low impedance path for fault current to flow back to the source. This ensures that overcurrent protective devices will trip quickly in the event of a ground fault, minimizing the risk of electric shock or fire. The grounding bus should be properly sized to handle the available fault current. The NEC provides guidelines for sizing grounding conductors and grounding electrode conductors based on the size of the service entrance conductors. In addition to connecting the workbench to the grounding bus, it is also important to ensure that all metal parts of the workbench are properly bonded together. Bonding involves connecting these metal parts with grounding conductors to create a continuous electrical path. This helps to prevent voltage differences between different parts of the workbench, which could create a shock hazard. When installing grounding and bonding conductors, it is important to use proper techniques and materials. Conductors should be securely fastened to terminals and buses using appropriate connectors. The conductors should also be protected from physical damage, such as abrasion or corrosion. It is also crucial to verify the integrity of the grounding system periodically. This can be done by measuring the resistance between the grounding bus and various metal parts of the electrical system. A low resistance reading indicates a good grounding connection, while a high resistance reading indicates a problem that needs to be addressed. In the specific scenario mentioned, the grounding bus has a resistance of 0.16 ohms to ground. This is a relatively low resistance, indicating a good grounding connection. However, it is still important to verify that all grounding connections are properly made and that the grounding system is functioning as intended. In summary, while the NEC does not explicitly prohibit grounding to a receptacle cover screw, the practice is strongly discouraged due to the associated risks. The NEC emphasizes the importance of using designated grounding points and ensuring that grounding connections are reliable and effective. Grounding to the building's grounding bus is the recommended method for grounding a workbench, as it provides a low impedance path for fault current and meets the requirements of the NEC. When working with electrical systems, it is always best to err on the side of caution and follow the NEC guidelines to ensure safety and prevent hazard. Improper grounding can have serious consequences, so it is important to take the time to do it right. It's important to remember that electrical codes and regulations are in place to protect people and property. They are based on years of experience and research, and they represent the best practices for electrical safety. If you are unsure about any aspect of electrical work, it is always best to consult with a qualified electrician. A qualified electrician has the knowledge and experience to ensure that electrical work is done safely and in accordance with the applicable codes. They can also help you identify and correct any potential hazards. Working with electricity can be dangerous, so it is important to take all necessary precautions. Always de-energize circuits before working on them and use appropriate personal protective equipment, such as insulated gloves and safety glasses. By following these guidelines, you can help to prevent electrical accidents and ensure the safety of yourself and others. In addition to the NEC, other standards and regulations may also apply to electrical work, depending on the location and the type of installation. For example, the Occupational Safety and Health Administration (OSHA) has regulations that address electrical safety in the workplace. It is important to be familiar with all applicable standards and regulations before starting any electrical work. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or other qualified professional before making any decisions about electrical work. Electrical safety is a serious matter, and it is important to take it seriously. By following the NEC guidelines and other applicable standards, you can help to prevent electrical accidents and ensure the safety of yourself and others. Always remember to prioritize safety when working with electricity.